Question 5 on a gravity assignment. The radius of planet X is 5.86 times 10 to the 7th meters and has a mass of 2.37 times 10 to the 26. What is the gravitational field strength on planet X? Gravitational field strength. So this is a pretty straightforward question. But before we do it, let's just see if we can hypothesize what the answer might be relative to Earth. So relative to Earth, this is the radius of Earth. This planet has, this is times 10 to the 7th. So is it a little bigger? No, it's not a little bigger. It's a lot bigger. It's 10 times bigger. The radius of this planet is 10 times bigger than Earth, essentially. Just as a rounded off number. What about the mass? This is the mass of Earth. And mass of this planet is 26. This is 24. So this planet is it a little more massive than Earth? No, it's a lot more massive. In fact, it's if you subtract the exponents, 26 minus 24 is 2. 10 to the exponent 2 is 100. So this planet is 100 times more massive than Earth, and it has a radius that is 10 times bigger. So the big question is, what's going to win out? Is it the 100 times the mass or 10 times the radius? And the answer may surprise you. So in terms of the question, it's very straightforward. 6.67 times 10 to the negative 11 times the mass of the planet. Divided by the radius, and don't forget to square it. Okay, so get out your calculator. 6.67 e negative 11 times 2.37 e 26 divided by, and I'm just going to put this thing in brackets, 5.86 E 7 and the brackets squared, and you get this answer. Which personally I find to be a little surprising. The gravitational field strength of this planet is about half that of Earth. And why? It's because of this. It's because of the radius. The radius is 10 times bigger than Earth, but remember you square it, so that has the effect, because it's an exponential relationship, that has the effect of reducing the gravitational field strength by quite a bit. Next question. A 70-kilogram astronaut is standing on a scale in a rocket accelerating away from Earth at 2 Gs. And remember, the 1 G equals 9.81 meters per second squared. What is the reading on the scale? So here's the scale. I'm just going to draw a Peabody diagram. You got the normal force pushing up. That's the astronaut standing on the scale. So the normal force is pushing him up. Gravity is pulling him down. And watch the video on elevator questions if you're confused about any of this. Therefore, the net force equals the normal force plus the force of gravity. And in all these questions, when it says what is the reading on the scale, it's asking for the normal force or the apparent weight. If it asks what's the apparent weight, it's asking for what's the reading on the scale. And so the normal force will equal the net force minus the force of gravity. Net force, mass times acceleration. Force of gravity, mg. The kilogram, what's the astronaut is how much? 70 kilograms? 70 kilograms, and they're accelerating at 2 Gs. So if 1 G is 9.81, then 2 Gs is double that. So it's 19.62, and that's going to be positive because they're accelerating up. The 9.81 is going to be negative because gravity is always going down. And so as you can see, the negatives here, this negative here, and this negative here will have the effect of becoming positive. And it means you're adding these two numbers together because yes, when you, the normal force on that scale is going to be really high. That's the reading on the scale is going to shoot up when you're accelerating at 2Gs. It's going to shoot up a lot. So stick that into a calculator. 70 times 19.62 equals plus 70 times 9.81. I just made everything positive, and I get 2,060 newtons, which is pretty significant. So if this person was just standing, if a 70-kilogram person is just standing on Earth, what will the scale read? If they're not accelerating or they're moving at a constant velocity, the scale will read 70 times 9.81, 687 newtons. So normally the scale would read this. That would be their apparent. That would be their weight. This is what the scale now reads, 2,060. So you're going to be feeling it when you're moving at 2G, accelerating at 2Gs. You're going to be feeling it. So you're not going to be, you're not going to show up all over yourself or anything, but yeah, you'll know you're moving. And then the second part of this question, which is not part of the assignment, but I think is important, says, what is the astronaut's apparent mass? And that's just how heavy or how much mass do you feel like you have when you're accelerating at this rate. And remember, so it's a 70-kilogram person, and they have this weight here. To find out what the apparent mass is, we're just going to use this formula here. Solve it for m, and this time we use the apparent weight. And we do that. 2060 divided by 9.81 equals 210. So that's a pretty interesting fact. A 70-kilogram person is going to feel like they actually have 210 kilograms of mass when they're accelerating at 2Gs. All right, onward and upward. Good pun. The gravitational field strength of, since the last one, the gravitational field strength of Neptune is 11.15 newtons per kilogram. How long would it take an 80-kilogram person to fall 30 meters on Neptune? So what have we got here? We've got G. How long? We're trying to find time. Would it take an 80-kilogram person, the mass is 80 kilograms, to fall 30 meters? So they're on Neptune and they're falling 30 meters. So the distance they're going to fall, oops, right there, is 30. Distance is 30. Okay, well, that's interesting. Those are interesting variables, aren't they? You've got a G, a T, an M, and a D, and there is no formula with those variables in it. However, you have to remember that G really is G is gravitational field strength, but is also acceleration due to gravity. And then you've got time and you've got distance, and we have to assume that you are starting from an initial velocity of 0. So if you look at it this way, this question is actually a very simple, not simple, but it's a kinematics question, isn't it? You've got acceleration, you've got time, you've got displacement, and you've got the initial velocity, and the mass is completely irrelevant. As we should all know, mass is irrelevant, right? You drop a cannonball and a ping pong ball in a vacuum on Earth, they both fall at exactly the same rate. So what formula has these 4 variables? It's Old Faithful. This guy right here, VI is 0, so that cancels out, leaving us with D equals 1/2 AT squared. Solve for T. I'm going through this quickly because you should have done this a million times. Minus 999,000. There it is. The square root of 2 times the distance. Now, if you want to be really, really correct, you should put negative because they're falling down. And then, of course, you should put the acceleration due to gravity also is negative. And then they cancel out. Stick that into your calculator. 2 times 30 divided by 11.15 equals, take the square root. Don't forget to take the square root. And there's the answer to your question. It takes you 2.32 seconds to fall 30 meters on Neptune. Of course, it's going to take you about a couple hundred years to get to Neptune, so you really won't care how fast you're falling once you're at Neptune. Okay, well, hopefully that'll help you out with the assignment, and take care.